Okay, so we have this function y squared equals 2x, and we're trying to find the exact point on this curve that's closest to 1 comma 4. And we're going to use calculus application of differentiation optimization to do so. So if you don't have Desmos, if you have Desmos, you might be able to guess the answer. But right now, let's think in terms of the inverse function, switching x and y. X squared equals 2y, divide both sides by 2. Y equals 1/2 x squared is a flattened parabola. So in terms of inverse, switching x and y, we can reflect this graph along the line y equals x and realize that it looks like the letter C. So here is the actual graph. You might want to punch this into Desmos. And you can see that this is going to be 1 comma 4 is about here. And you can guess, just looking at Desmos, that the answer is going to be 2 comma 2. However, when you're talking about distance and minimizing distance, we know the answer should be around, maybe perhaps around here, where there's a 90-degree angle. We don't want to pick a long distance this way. That's going to be too far. We want to pick something short, perpendicular distance. So what is the famous theorem involving this triangle, right triangle? We're going to use Pythagorean theorem. So d squared, that's like your c squared equals a squared plus b squared. D squared is going to be the bottom squared plus the top squared. And the bottom squared is going to be the bigger number minus the smaller, which is going to be x minus 1. So it's going to be x minus 1. This value minus this value squared plus this minus this, which is going to be y minus 4 squared. You always have to go corresponding in the same direction. So what we have here is the Pythagorean theorem. And what we're doing now is we're going to, instead of dealing with two different variables, we're going to deal with the same variables. We're going to stick in the language of y's. So this might be a bit confusing because we're always used to y's and x's or certain letters in our head, but let's just focus on d's and y's. So we're going to substitute x here. We know that y squared equals 2x. Divide both sides by 2. We get x equals y squared over 2. Replace the x with this y squared over 2. And let's see what happens. So now we have this expression involving d squared equals this one here. If you really want to think about the distance between that point 1 comma 4 and the curve, you can square root both sides. And so we have a nice distance equation. We're not going to deal with negative distances. So we're not going to go, when you square root both sides, normally you say plus minus, but we're just going to deal with a positive version. So the goal is to minimize this. We're trying to find the derivative. Now you could think of the derivative, you have a square root here. This is the same thing as exponent 1/2. And we want to set derivative equals 0. But let's think some other way as well. So what we're trying to do here is we're trying to find this value, the variable's value, this y value, in which the derivative equals 0. Now I know that we're more used to x's and y's, so on this same graph here, instead of d's I'm writing y, instead of y's I'm writing x's. On Desmos, if you visualize what's happening here, y equals square root of this business here, it looks like this curve over here. And what we're trying to do is we're trying to find the minimum, where the derivative is 0 right here. So we're trying to find the x value in which the minimum occurs. Similarly, for this question up here involving d's and y's, we're trying to find the y value. So we have this beautiful graph here. It looks like a happy face. Now think about what happens when you square the graph. Each and every single individual y value, if you square it, because all these values are positive, generally it's going to end up being bigger. For example, pretend the value was 2. What's 2 squared? It's going to be 4. Pretend the value was 3. What's 3 squared? It's going to be 9. So generally all these points are going to be higher, and if you actually square this, it's going to be another happy face. It's going to move up. But yet, generally the minimum value squared stays pretty small, so it's not going to grow as quickly as these other bigger numbers. So therefore, we're still end up figuring out the same x value, or in this particular case, if we square both sides, the same y value. So we're still solving for this variable here when we square this graph. Okay, so this is the distance we're concerned about. We'll focus back on d's and y's. And so when we square both sides, just like how we reasoned previously, we're still trying to attack this y value, which is going to be the y value, particularly at the minimum value that we're interested in. So we're going to define f of y. We're not dealing with x's, we're dealing with y's. So we'll just think of it like on decimals, like the x's. We're dealing with this function called d squared. We're going to square both sides. It's fair. So f of y will be this graph. It happens to be squared, yet when we're focusing on the derivative equals 0, it's going to result in the same y value for the reason we just explained previously. So we're trying to find the derivative of this function here, d squared. So what is the derivative? We're simply going to use power rule. You drop the 2 down in front. You decrease the exponent by 1. But don't forget about chain rule. You need to find the derivative of the inside. So the derivative of y squared over 2, we're going to try to figure it out here in the next step. Okay, so what about the second part? This is going to drop the 2 down, 2y minus 4 to the 1. And then if you want to multiply by the derivative inside, the derivative of y is just 1, so we're not going to bother writing that. Okay, we're going to simplify this here. It looks like the exponent 1 disappears. And the derivative of the inside here, so for the y squared, the 2 drops down. 2 divided by 2, they cancel. So as you can see, here is a 2, and here's the 1/2, and they cancel. And then we have the y, and then the 2 decreases by 1, and there's the y to the 1. And the derivative of a constant disappears, so we're not going to bother writing down 0. So we're just ignoring the exponent 1 here. We're just doing distribution, 2 times y, 2 times negative 4. So for this part here, it becomes 2y minus 8. And we're just cleaning things up here. We're distributing. This times this, the 2's cancel out. This times this becomes negative 2. And don't forget the brackets here, because this is all being multiplied. You can see that these cancel. We have y here. And now we're doing distribution. This times this becomes y cubed. This times this becomes negative 2y. We're just copying this down here. These y's cancel. And so therefore the derivative is going to be y cubed minus 8. That's great. And we're setting the derivative equals 0. Because we're trying to solve this variable in which the derivative is 0. It's a happy face. We're trying to figure out that y value. Throw the 8 over, cube root both sides, and we have the y value is 2. So this is the specific variable's value in which we found that minimum. The derivative is going to be 0, which is the minimum value. So y equals 2 is going to be the derivative of 0 as a critical point. You set up your boundaries. If you really want to test it out, you can plug in some test points. So to the left, we're going to plug in 0. To the right, we're going to plug in 3. F prime of 0 is going to be 0 cubed minus 8, which is negative 8. It's going to be downhill, decreasing. And then you plug in the value into the derivative formula. It's increasing, and clearly this is a minimum. So what we can say is that f prime of y is minimized at y equals 2. Now recall the original question. It says y squared equals 2x. Plug in the specific y equals 2 value into this formula, and you'll find the x value. So 2 comma 2 is the closest point to the graph. So from now on, when you get a question like this involving minimum distance, don't forget about Pythagorean formula, Pythagorean theorem.